Okay, so today we are starting a new module. This module is on multivariable functions and partial derivatives. And this section is functions of several variables. And so we've always looked at functions, y is equal to a function of x. So in Calc 1 and 2, actually, and Calculus 2, we have y is a function of x. And so therefore, here is, well, it doesn't matter. So here is y and here is x. And if I give you an x value, you give me a y value, and I can draw a function y, which is a function of x. Okay, so in Calc 3, okay, this level of calculus, we now have the entire XY plane as a domain. So we could consider now let's say a function v, which is equal to pi r squared h. So here v is some function of r and h. Or I might consider f to be a function of x and y, where f of xy looks like x squared plus y squared. Okay, so now we have functions of more than one variable. So functions of two variables are easy to draw. Okay, so a function of two variables, z equal to f of xy, that's easy to draw because I define whatever my function is. I go locate my point in the x direction, then find my point in the y direction. And so here is the point xy. And then it has a z value, f of xy in 3 space. Now, functions of more variables become more difficult. All right, you can't draw them because they're not in 3 space. Okay. So I'm going to let D be a set of what we call n tuples. So D is the set of all things that look like x1, x2, all the way up to xn. So that's an n tuple. And here all the xi's are real numbers. Okay. So now we're talking about a real valued function. We've talked about vector valued functions for quite some time. So now we want to talk about a real valued function. So a real valued function we can call it W. And W goes from D to R, all right, is a rule that assigns an element of D to a real number. Okay, so for example, W can be a function of x1, x2, all the way up to xn. So W is a real number, all right? And this is true for everything that's in D, all right? So the set that W acts on, which is D, is the domain. Or I should say the domain of F. And then W, which is F of something, is in the range. And so the set of all W, the range is the set of all W that are F of something this is the range. Of F. Okay. So the xi's, so this thing, x1, x2, all the way up to xn, are the input variables. And W, which is F of that thing, is the output variable. Okay. All right. So here's the easy example. So here's the example. So F is going to go from R3 into R by F of X1. F, let's make it XYZ, make it nice and easy. F of X, Y, Z is the square root of X squared plus Y squared plus Z squared. Then F of 304 is the square root of 3 squared plus 0 squared plus 4 squared, and that's the square root of 25. So that's just 5. Okay. All right, so that's how you just handle a function of more than one variable. All right, so one of the things we need to do is we need to look at the domain of these functions. So the domain of these real valued functions. So generally finding the domain is easy. The two things that make the domain hard I'll say cause you to think are square roots and reciprocals. Other than that, most everything else is pretty clear. Sometimes logarithms. Things that generally have issues with the domain. Okay, so here's an example. Okay, so the first one, so here's the function. Here's the domain. And then here's the range. So let's look at something like W is the square root of y minus x squared. Okay, so clearly it's a square root. So y minus x squared has to be greater than or equal to 0. So y is greater than or equal to x squared. So that's the inside of a parabola. And the kind of numbers that can come out of there are only positive numbers or 0. So the range is the interval from 0 to positive infinity. Can't get anything negative out of there. How about W is equal to 1 over x times y? Well, the domain is the set of all points where x, y is not equal to 0. So x can't be 0 and y can't be 0. And I can get everything out of here except 0. So I can get minus infinity up to 0, union 0 up to positive infinity. How about W equal to the sine of xy? Okay, I can put any number in there. So the entire plane, the entire xy plane can go in there. But only numbers between -1 and 1 can come out. The last one, how about the log of x plus y? Well, if I look at that, that says that x plus y has to be strictly greater than 0 because I can't take the log of 0 or a negative number. So that says y is strictly greater than the opposite of x. And so that's half of the plane along the line y is equal to -x. All right, so this is actually half the plane. But if I were to draw it, I would have something like this. I would have y is equal to -x. So that looks like this. And then it says y is greater than -x. So therefore, I would have this whole region shaded forever. So it's half the plane, but it's half the plane like that, where that just keeps going. Okay. So that's functions of two variables. That's supposed to be an example. So here's an example of a function of three variables. Okay, same scenario. I'm going to have a function. Then I want to have its domain. And then its range. So here's the function. This is the domain. What did I write up there? I'll get ready to say, I don't remember writing f of x. I wrote function. And this is the range. Okay. So let's say W is the square root of x squared plus y squared plus z squared. So this is entire 3 space. Anything can go in there. But the only thing that comes out are positive numbers or 0. Okay. W is equal to 1 over x squared plus y squared plus z squared. And so everything is viable to go in there except for the 0.000. And what can come out? Well, you can get positive things that can go from 0 to infinity. How about W is equal to xy times the log of z? Well, clearly x and y can be anything, but z has to be positive. So what does it mean for z to be positive? Z to be positive, so here's z, and down here, so z to be positive is the upper half space. Okay, octants 1, 2, 3, and 4. And these numbers can be, x and y can be anything. So I can get any real number out of there. Okay. Let's talk about what it means to have a region. Okay, so a region is going to be a set domain, all right, in the XY plane. I won't even call it a domain. I'm going to call it a set area in the XY plane. So here's the XY plane. And I'll draw my region. Okay, so that's my region R. Okay, so that's my region R. So now I want to define a point, another definition, a point x naught, y naught is an interior point of a region R. All right. If it is the center of a disk that fits, that lies directly in R. Okay, so this point right here is an interior point because I can draw a disk around it, and that disk is completely in R. Okay, so it's an interior point. Definition. A point X naught, Y naught is a boundary point of the region R if every disk about the point X naught contains both points that lie within R and points that lie outside of R. So now I can choose a point here. And no matter how small the circle is I draw around it, I get points inside R and points outside of R. Okay. Definition. A region is open if it is only contained, if it only contains interior points. So what do I mean by that? So here's my region. That's my region. So any point I pick and draw something around it is still contained inside. And so it only contains interior points. Okay. The boundary definition, the interior of R is made up of all its interior points. Definition. The boundary of R is made up of all its boundary points. And definition, man, a bunch of definitions, honey. Woo-wee. A region is closed if it contains all of its boundary points. Okay. So a region, so now let's talk about boundedness. A region R in the plane is bounded if it lies inside a disk of fixed radius. So if you have a region and you can draw a circle around it, then that region is bounded. And a region R in the plane is unbounded if it is not bounded. Okay. All right, so now these same definitions go for three-dimensional things, okay? So instead of a disk, we're going to talk about a sphere. Okay, so all of this was 2 dimensions. Well, these definitions. So we're going to move now to so let's move to 3 dimensions. All right, so we're going to say the same thing. So now we're going to have a region D, which is considered a 3-dimensional region D. Okay, so now I'm in 3 space. So now I have a region that looks like this. Okay, so that's some 3-dimensional region. Okay. So a point now we have X naught, Y naught, Z naught. All right, is an interior point of a region in 3 space D in 3 space if it is the center of a ball that fits entirely in D. Okay, so let's choose this point right here. And then I can draw a ball. Oh, that ball's supposed to be closed, open. Shucks, 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 shucks. Okay, so if I can draw a ball around it and that whole ball stays in the region, then that's an interior point. Okay, definition. A point X naught, Y naught, Z naught is a boundary point if every ball containing the point X naught, Y naught, Z naught contains points inside and outside of D. Okay, same definitions as before, except now we're using balls. Okay. So you can extrapolate the definition. All these definitions are the same. Okay. All right. So now I want to talk to you about what we call level curves. And level curves are actually pretty cool. I like level curves. Okay, so let's talk about level curves. Okay. Level curves. Okay, definition. The set of points in the plane where a function f of xy has a constant value f of xy equals c is called a level curve of f. Okay. Okay, here's an example. So here's my thing in 3 space. And here's a level Z is equal to some number C. So at that point, there may be a curve of the function exactly at that height, for f of x, y, exactly equal to C. Okay, so here's an example. Z equal to f of x, y is equal to x squared plus y squared. This is a paraboloid. Okay. Okay. Okay, so here's the paraboloid. It just keeps going up. The point Z equals 0, Z equals 0 corresponds to that point. In other words, Z equals 0 is x squared plus y squared is equal to 0. The only way that can happen is if x and y are both 0, and you get Z is equal to 0. Then, if you do Z is equal to 1, so Z is equal to 1 is at this height, you get a circle of radius 1. So Z is x squared plus y squared, and that equals 1. You get a circle of radius 1. And that's your level curve. So I'm taking the blue picture, the blue thing in the 3 dimensions, and pushing it down on the 2 dimensions. Now, this is Z is equal to 4. Well, that's just a circle of radius 2. And then I can do another one. I need to bring that one up higher. Okay. This is z is equal to 9. Z equals 4. Z equals 2. Z equals 0. If z is equal to 9, okay. So now z squared, z equal to x squared plus y squared equals 9. So all of these are different values of c. The first one is c is equal to 0. That was that one. The next one is z is equal to 1. And that was that one. Then we had z equal to 4. And that was this one. And then we got z is equal to 9. And that's that one. So the level curves are what happens if you kind of like slice the paraboloid at z equals 9 and then look down. You're going to see a circle of radius 3. So those are the level curves. Okay, here's another one. F of xy is equal to 8 minus x squared minus 2y squared. Okay. I swear this one is impossible to draw. It's actually not. Doesn't have to be impossible. Okay. I'm not going to need all this. I need to draw a straight line from here down to there. That helps. Then I'm going to draw this line. Going to come down like that. And then this line comes down like that. So that lets me think that this one's out too far. And that one's actually supposed to go all the way to the x-axis. Okay, there we go. And then I can draw parabolas. That's one. 2, 3. Okay, that's actually pretty darn good, I think. Okay, so this is f of xy equals 8 minus xy x. So this is 8 up here. Okay. So if parabolas, I think I got this written wrong. It is written wrong. There's no y squared. I knew something was wrong. Okay. So now if z equal to 8 minus x squared minus 2y squared, 2y is equal to a constant c, then you end up with 8 minus x squared minus c equals 2y. So y is equal to 1/2 x squared plus 1/2 of 8 minus c. And that's exactly what you see. No, you don't. No, you don't. If z is a constant, oh, that's why. Okay, this is supposed to be minus x squared. Now I see it. Okay, so if z is a constant, you get upside down you get parabolas. So this parabola right here, obviously, is z is equal to 0. So that parabola is y is equal to minus 1/2 x squared plus 4. And if z is equal to 2, then I'll get y is equal to negative 1/2 x squared plus 3. And so if I were to draw them in the xy plane, that's y and this is x, I would get the first parabola. That still looks awful. I can't, just can't. But the next parabola looks like this. Why is my hand so shaky? Ooh, these parabolas on the right, this side are horrible. It's better. Okay. So that's what you would get. Anaya, are you there? Anaya,
Yes, I'm still here.
okay. If F gives the temperature at a location then the level curves are called isotherms. And you've seen those on the weather map. Those are pretty easy. Okay. So those are level curves. Level curves come from functions of two variables. Okay, level surfaces, on the other hand, come from functions of three variables. Okay. So that means we let W, which is a function of X, Y, and Z, equal a constant. And so just like you get different level curves for different constants, so each level curve here was at a certain height, and it gave a different picture on the XY plane. Each level curve here was at a certain height, and it gave a different picture on the XY plane. Well, now, every time Z is a constant, you can get a different type of surface. So your surface can change, okay? So here's an example. F of X, Y, Z is equal to X squared plus Y squared plus Z squared. Oh, minus Z squared. So that's my function. So now I want to describe the level surface for, I think in 3D, I let the constant equal K. I don't know why, but for K equal to 4, -4, and 0. So for these different values of the constant, we might see different values for the surface it makes. Okay, so the first one, we get A, and we let K equal to 4. So that means we have x squared plus y squared minus z squared is equal to 4. Okay. And if you remember for this one is a hyperboloid of one sheet. So when z is equal to 0, you get x squared plus y squared equals 4. That's a circle. When y is equal to 0, you get x squared minus z squared equals 4. That's a hyperbola. And when x is equal to 0, you get y squared minus z squared is also equal to 4. And that's also a hyperbola. So for this thing, we get a circle down here. And then we get a hyperbola. And another hyperbola. And then we have the other hyperbola. And then we have the last hyperbola. And then you're also getting other circles. Why do you do this? You unnerve me. So you get a hyperboloid of one sheet. So when k is 4, you get a hyperboloid of one sheet. Now when k is equal to -4, you end up with x squared plus y squared minus z squared is -4. But that looks like z squared minus x squared minus y squared is equal to 4. We already know that's going to be a hyperboloid of two sheets. Then so we get a hyperboloid of two sheets. So for k equals 4, -4, we get a hyperboloid of two sheets. And the last one makes perfect sense. So let me tell you what happens here. So look at this. This is k is equal to 4 and k is equal to -4. So as k gets smaller and smaller and smaller, this thing shrinks in. And then all of a sudden it pops apart and splits into 2. So at k equals 0, which I should have done next, but I didn't, so that's all right. You get x squared plus y squared minus z squared is actually equal to 0. So that is x squared plus y squared plus is equal to z squared. And that's a cone. So that's kind of cool because this now looks like this. Okay, so kind of see what happens here. For positive values, you get a hyperboloid of 1 sheet. As the numbers decrease, the thing goes from looking like a hyperboloid of 1 sheet into a cone. And then as they go negative, it pops open and becomes a hyperboloid of 2 sheets. Okay, so that's it for that section.